good. But anyway, because of handwriting. But anyway, the results were quite nice, I would say. So, so there we go. With the lecture, we finished with. So yeah, before we go, tomorrow we have, because on Thursday I have to be out of Wrocław, probably. I'm not yet sure, but probably. So the consultations, the project is tomorrow. So tomorrow is the first Friday this week. So we have tomorrow the project. We have the project tomorrow at, it was 11 or 1, I don't remember. Or 1. At 1. Because you finish some classes. Yeah, we finish some class tomorrow at 1. So the project meeting is tomorrow at 1 in my room. So it was on Thursday in my room already, so 244 for those that do not know how weren't present there. And I placed the folder as promised on ePortal. So there is on ePortal a folder for the project. So if you are ready with your PCBs, because some of you are already ready with the PCBs and you want the PCBs to be manufactured physically, as promised, so if you finish your project, if you finish your PCBs by Christmas, then you upload the project into this folder. So please upload, so they will be classified with your names. So this is students folder on ePortal. So I will have Gerber files because I want to have Gerber files, of course, not the projects themselves, because for the production I need Gerber files. So please generate all the Gerber files necessary and put the project in the projects folder. We have next class on Wednesday, because there is a Monday on Wednesday. So we have 2 Wednesdays and Fridays this week. So next Monday is on Wednesday. However it sounds. Any questions? Any questions? So off we go, because we have already 45 minutes delay. Yeah, we finished somewhere here about the ADC, so it's not a course about signal processing. So just a brief reminder about the terminology. So first we have a signal, then we have a signal, we sample the signal, and here we have a sampling frequency, so TS. Then when we have the signal sampled, then the signal is held during for the sampling, for the measurement itself to take place. So we have a sample and hold. That's why when we talk about microcontrollers and about ADC conversion, we always talk about sample and hold circuit, because there must be some holding, sampling and holding of the value, so that there is a time for measurement itself, for conversion from the analog domain into digital one. So that's why sample and hold always there. Remember important things from the practical point of view. If we go back here for a moment, important thing from the practical point of view are those 2 times. So TW and TS normally, because this is the whole sample time, and then the period, the conversion period. So these are 2 things that are always characterizing the ADC converter when we talk about it in microcontroller or even outside, because the ADC converters today we have both inside the microcontroller or as a separate chips. And generally, the shorter TS, the better. That's always. So the shorter is the conversion, the better, because it's always better to convert something in 1 microsecond than to do it within 1 millisecond or 10 milliseconds. It's always better. But it's not that obvious about TW, because when we talk about the sample time, sometimes longer is better. And the question to you: when longer is better? What can we achieve by setting longer sampling time? Normally in microcontrollers, we can regulate the TW.
Higher input impedance?
Yeah.
Maybe higher resolution.
Or high resolution because of what?
More digits.
Now, high resolution because of what?
Maybe at least with a slow converters, you charge a capacitor, so it charges longer time, so you can estimate this.
Yes, but as I said, it's not exactly. Of course, it increases the resolution, but not in a direct way. In an indirect way. What happens when we sample longer?
Higher SNR?
Good point, good shot. Higher SNR, because we've got average the signal. So signal to noise ratio increases, in fact, with longer sampling time. Therefore, we have higher resolution. That's how it works. Because we average the signal longer. Normally, the noise of the signal, from formal perspective, the noise of the signal has Gaussian shape. So it's a normal distribution, or Gaussian distribution, which means that it averages. Very nicely, it averages. So if we extend the averaging time, so increase the TW here, then we have a higher SNR, which means that we can get high resolution, that we can obtain high resolution. Okay, in case of resolution, so again, the terminology that we talked about, remember that the resolution itself, so delta V here as a marking, is the range voltage by the amount of states. So when we talk about what the N is the resolution, how we classify the ADC converters. So what does it mean? That if we talk about 8-bit microcontroller, 8-bit ADC converter, it has 256 states. If we talk about the 10-bit converter, it can discern 1024 states. Of course, the resolution is normally so-called reference voltage, not the resolution, but VR is normally a reference voltage. So the voltage that we connect to a microcontroller at the reference input, like that. So microcontrollers always have a reference input to the ADC converter. It's separate from power supply. Sometimes in small microcontrollers is the same, but usually the reference input is separate from the main one. Again, the question why? Why the reference input, voltage reference input, is usually, even if we set the same voltage, even if 3.3 volts here, 3.3 volts here, but usually the reference voltage is a separate input. Why? Why the reference voltage is separate?
So it's not affected by the primary voltage?
By the noise. On the primary voltage. Because on the primary voltage, you know, we have a digital circuit, we have a clocking, we have switching, we change the value of the registers, which means that there is a lot of switching, and there are various current spikes. So those current spikes are present on the voltage. That's why we are using decoupling capacitors to get rid of those spikes, so to reduce those spikes as much as possible. That's why I mentioned that the decoupling should be as close to the microcontroller inputs as possible, actually, to get rid of those current spikes. And in case of ADC voltage, there are not so many spikes. So depending on the technology, but still the ADC, of course, is not as noisy. It's far less noisy than the major digital registers and all this core memory and DMA, whatever is there inside the microcontroller. That's why usually we have a separate voltage. We don't need to supply analog here. It's enough to supply a digital, but we have to filter it back. And usually we have a separate voltage. Remember then, if we talk about parameters of ADC converters, that the resolution doesn't mean the precision. So it's always that it's in metrology. So this is general rule. So on Prusa, you did have the classes with metrology, so they should have told you that there is a difference between the resolution and precision, and that's actually here as well. So if we talk about 8-bit microcontroller, it means that the resolution is 1/256 of this voltage. But the accuracy may be 1/256, but maybe better. It can never be maybe less. It can never be better. So if we have a resolution of 1/2 of delta V, accuracy is never better. It can be worse, but it's never better. That's the resolution of the ADC. That's also important to know. What the accuracy depends on, we don't have actually so much time to play with it, because really we are not about ADC here discussing, but about rather microcontrollers. But the major limiting factors, so there are two major limiting factors. The factors limiting the accuracy of ADC converters today. Factor number one, noise. Various noise. Various noises come. Usually noise coming from the reference voltage. Second factor is linearity. Depending on the technology, the linearity is not perfect of the ADC converters, and usually we lose a couple of bits of resolution to the non-linearity. How much do we lose? If we talk about 8-bit converters in microcontrollers, usually they are linear within 8-bit range. So usually the 8-bit converters have linearity below or better than the resolution. But if we take a 16-bit or even worse 24-bit converter, such converters are present in microcontrollers. Those converters usually have linearity even 4-bit or 5-bit, which means that the resolution of 24-bit converters in microcontrollers have, of course, 16 million states, because 1 to the power of 24, 2 to the power of 24. But usually the accuracy, the linearity is 5-bit or even worse, which means that the real accuracy of 24-bit converters is usually 18-bit, 17-bit even. So that's the problem with higher accuracy converters. So be careful. Of course, 8-bit works very nice. 10-bit works so-so, but 12, 14, 16-bit in microcontrollers work even worse. On the chart there was the sampling frequency, and in case of the sampling frequency, here is the rule is the faster the better. Why the faster the better? Because then we can of course slow down. This FS. We can slow down the microcontroller, or we can regulate the FS. Of course, if we can do more, then we can do less as well. And then with this FS, with the regulation of the FS, we can start playing with so-called aliasing. Again, it's not the time nor the space to talk more about the ADC aliasing, but in general, I like it very much, really, to be honest. The aliasing, how fascinating it works. How fantastic it works, in fact. Because what's so fabulous here? The fabulous thing is that, first of all, we can sample it at much lower frequency. We can get the signal from much higher frequency, and we can alias it back to the main band. We can do some so-called undersampling, which means, in other words, that we can have much slower ADC converter with very small data rates, and still we can sample, we can get the information from the signal which is very far in the frequency. For example, you can sample a frequency at 1 megahertz and get the signal from 100 megahertz band. That the information hidden, you can read the information hidden between 100 and 100.5 megahertz. Because we sample at 1 megahertz here, but the signal here, so it really goes to infinity. Of course, it's not possible or practical to, there are some small limitations, but still, that's fantastic, that's fabulous that we can alias this. So the aliasing is generally harmful, to be honest. So generally it's harmful because it has also the dark side about the aliasing. So what's the dark side? Yeah, we have the signal here in the zones on the main one. Because remember, we have the Nyquist criterion, which means that we have to sample twice as fast. So that's why FS is here, and our useful band is zone 1 at this line. So we have nice signal here that we want, and we have some noise. Yeah, from here on. So here is just half FS, and the rest is just noise. And if we do nothing with the aliasing, if we don't protect against aliasing, then the harmful thing is that all the noise cut from this zone 2 to infinity will alias back to our signal. And that's actually what's happening. That's actually what's happening. So if you don't believe me, try. If you don't believe me, try. Right? Take microcontroller and try. It's really fascinating to see that you make the FS, let's say, 10 kilohertz. Let's not go into megahertz. You make FS 10 kilohertz, and so here is 5 kilohertz. And then you make a tone, 1 kilohertz tone here, and let's say 8 kilohertz. So 1 kilohertz tone, you take a generator, 1 kilohertz, 8 kilohertz, and sample at 10 kilohertz. In the microcontroller, when you make the FFT, you will get back 1 kilohertz and 2 kilohertz tones. So if you are an amateur, so what the fuck? 2 kilohertz, where is it from? It was 1 and 8, and I get 2. But the 2 comes from here. It falls back. It has strong, and so you have to know what you are doing, then it works. But if you don't know what you are doing, then it doesn't work. But that's the magic. Simple, but very nice. Anyway, that's why we use anti-alias filter, and that's why, in case of microcontrollers, always, in any ADC, but microcontroller as well, always there must be anti-alias filter. It's not an option. It's a must. Anti-alias RC, simple filter. But we have to make a low-pass filter to get the zone 1. Or if you want the aliasing to be used, band pass. So then, for example, we want this zone, so then we have to make a band pass at the input of the ADC converter. It's a must. It's like a decoupling capacitor at any power supply input, anti-alias filter, any input of ADC converter, any input in microcontroller. So this is really a requirement. So an error is this, or a fault if it is not used. Okay, yeah, that's maybe not so important. Okay, let's go. What are the methods of the ADC converters? What are the constructions of ADC converters that we can find in real life? We can find in real applications. So couple of dual slope converter. So the most important, I would say, from practical point of view, dual slope converters, flash converter, sigma delta converter, and SAR-DAC, successive approximation converter. Also, we can convert from analog to digital through such strange methods like voltage to frequency, for example, charge balancing, blah blah blah. That's not important. The first four are important, in fact. So we have dual slope, flash, sigma delta, and SAR-DAC, SAR ADC. First, the least important out of these four, from practical point of view, again, the ADC converter. How does it work? We are charging and discharging this circuit. So actually we are charging it and discharging. We know the R, we know C, which means that we know RC. And then we are charging and discharging. So there is a zero detector, and we measure the time is measured here of the charging and discharging, discharging time, giving us, so that's why dual slope, because we've got two slopes. We've got two slopes. The method which is slow, so the advantage of this method is that it's slow, and unfortunately we need precise components. We have high accuracy, we have the results of conversions, really not very noisy, so we can get nice resolution, but from practical point of view, the dual slopes, although they are in use, they are not really present in microcontrollers, so they are usually outside. They're usually as separate chips. We can also build them by ourselves. This structure is not very complex, so we can build it. So this is just one DPST, SPDT, single pole double throw. So SPDT switch, tape, and simple op-amp, and that's it. But still, this is not preferable way of conversion. Tape number 2, flash converter, where we have a ladder of resistors, ladder of references, and again an array, we can say, a line of comparators, analog comparators, where the comparators are comparing the value of the input signal to certain to the references that we get from the ladder. And then we have a decoder that decodes these zeros and ones, because the signal will change the number of ones, and it's decoding it into a binary value. Flash converter, the name, which again, so this is the second tape which is popular, but not really in microcontrollers. Where can we find it? Because what's the advantage of this converter? Here it is. The advantages of this converter is that it is very fast, and we can use it, and it is present usually in oscilloscopes. Or this is the major type of conversion, because it's very fast. The problem is that because it requires so many op-amps, because there is 2 to the power of n of thresholds, then it's very expensive. Also, it prone to produce glitches in the output. Unfortunately, each bit requires twice the number of comparators. But take a look. It's very fast, but for 8-bit resolution, it's usually 256 comparators. So for 10-bit, it's 1000. So it's really sick value. But still, with this converter, we get into gigabits per second. Gigabits per second. That's the difference. In dual slope, we talk about kilosamples. Here we talk about gigasamples. Now, mark the difference. Of course, the price, of course, the resolution, because in dual slope we can count on 12-bit resolution. Why not? 14-bit as well. Here, usually it's 6-bit, 8-bit. It's really expensive to get 10-bit flash converter. But still, they are. Although they are not within a microcontroller. What we have in microcontrollers usually are the last two tapes. So sigma delta and SAR ADC. A sigma delta is both are kind of loop converters with feedback in their structure. In case of sigma delta, we've got a 1-bit ADC. 1-bit ADC, that is the output of the ADC, a DAC, because this is D to A, the digital to analog. The output of the DAC is compared with the input. And the difference between the input and the output is the integrated and compared, and then is placed at the input of the DAC converter. This gives us a stream of bits. This gives us a stream of bits. Depending on the input voltage, the stream of bits is more. There are more zeros in this stream or more ones in this stream. So if the voltage is 0, then we have only zeros. If the voltage is maximum at the input, we've got only ones. If the voltage is somewhere in between, we've got a stream of 0 ones or kind of 0 1 1 0 1 1 some structure. Then we can take a look. This is a single lane. This is a single bit stream. So there must be some decoding circuit. And the good thing about the sigma delta is that, okay, you want 4-bit precision, we take those 4 bits. You want 24-bit precision, we take all 32 bits, 24 bits. And that's how that's the major advantage of sigma delta. So the resolution is really chosen by us, chosen by the user. So we can choose the resolution because we've got just a bit stream which is dependent on the value of the signal, on the voltage of the input signal. So the advantage of the sigma delta, high resolution, no need for precision components, which means that it's cheap. So high resolution, low price. Problem is, of course, that it's slow, because what's the problem with slow? Why is it slow? This is slow. Here it is hidden, because this is filter. Integrator is a low pass filter, in other words. So this is slow, and of course the integrator must not be too fast, because it will be too noisy and we will have a lot of jitter. So it has pros and cons. So it's cheap, it's high resolution, cheap, but slow. That's the problem. We can find it inside the microcontrollers. So when we talk about 24-bit conversions, about 18-bit converters inside microcontrollers, they are usually sigma delta. Slow, and we have limits of frequency of bandwidth, but they are very cheap and pretty long and pretty accurate. Yet today, major ADC converters in microcontrollers are composed based on the SAR ADC idea. Here the idea is not that far from the previous one, because we also have a DAC, we also have a loop, although here the loop is anti-clockwise compared to the clockwise before. But here we have the structure, so the complexity goes more into DAC. This time DAC is not single bit, and we are not approximating, we are approximating in a loop, but we are not just approximating by changing one bit, but here we are approximating, setting the position of each bit in a loop. So we have a certain number of approximation cycles. That's why successive approximation, because we approximate the output value by adapting bit by bit. So from the most significant bit to the least significant bit, the values of the bits. Here we have the sample and hold. So the hold has to keep the signal stable for the time of the approximation. Already from this we can see that it's also not very fast, because it requires a few clock cycles. So we can't count on gigasamples per second like in Flash. ADC. Here we can count on megahertz, mega samples per second, because that's usually the case. So for in case of sigma delta, usually it's kilosamples, a few kilosamples at maximum, maybe tens of kilosamples sometimes. In case of SAR ADC, we go into megasamples. So in microcontrollers, usually it's about 10, 5, 10, 20 maybe megasamples, not more. That's more than enough for majority of applications. So if you want something faster, you have to usually take some external flash tape or SAR ADC, but external one. In microcontrollers, usually it's about a few megasamples in case of measurement. Oh, here it is. Here is the slide I wanted. So take a look. We've got the analog input, and then schematically how it works. So schematically, there is a testing of the most significant bit, and then younger bits, and then we've got the value, some value read, some digital output, and then depending on the input, of course, the final value will be different. But the approximation is always going on. Still, we need some time for approximation. We need some time for the DAC to settle the output. So that's why the SAR ADC is not as fast as, for example, the flash. So, finalizing the ADC in the ADC tapes and the features of SAR ADC, couple of high-speed and reliable measurements. The accuracy is maybe not the best one, but in general, the good trade-off between speed and cost, and that's why this is really most popular right now in use. Speed limit is usually a few megasamples per second. In case of resolution, 12-bit, 10-bit precision, 10-bit, 12-bit, 14-bit, 16-bit, up to 16-bit actually, we can find it in practical application. So here is the comparison between the various tapes. So dual slope, medium resolution, so from 12-bit to 18-bit flash, smallest one yet much faster than the other from the comparison. SAR ADC between 8-bit and 16-bit, and sigma delta, the largest ones, so up to 24-bit resolution. Better resolution at 24-bit is not practical. So in microcontroller systems, the noises are too high. So because theoretically with SAR ADC you can go further with sigma delta, because with sigma delta it's not a problem to have, let's say, 32-bit resolution. Why not? But the 32-bit resolution, then the linearity and the noise, the non-linearities and the noises cancel this high resolution. So there is no sense, and in practical application, I never maxed 32-bit resolution. Still, minded 24-bit resolution is really 16 million states, which means that with the reference voltage about 3 volts, we go down to microvolts. Microvolt is really very, very low value. So normally the noises, thermal noises, and various EMIs, electromagnetic interferences are much higher. Okay, and then how to use it? Why we are using ADC? Because we have, we have the ADC, we can have as a separate chip. And when we design a PCB board, when we design a device, we have a choice. We can take a microcontroller and the external ADC with good quality, high speed, and so on, and very nice case and low price, let's say, and we can take something built in a microcontroller. What's the major advantage of the microcontroller, of the ADC in a microcontroller? The major advantage is that it's integrated inside, which means that in order to read the result, in order to modify, to configure it in a way, it is for us, from our perspective, enough to write some value in a register. So we don't need to configure SPI, UART, I2C, I don't know, USB, Ethernet to communicate with anything, which takes time. We have everything integrated, and this is the major advantage. Second advantage is, of course, price, because we already pay for it. So the major cost of a chip, of an electronic chip is, it's not the silicon itself. The major cost of the silicon, of the integrated chip, is the package and distribution. It makes the cost, not the silicon itself. The silicon, of course, the factory, so the Intel factory or Intel machines is very expensive, or some support TSMC. But there is a large wafer, so if they cut it into pieces, the single cost is very small. The cost makes the package and distribution. So if it is integrated, of course, it's cheaper because it's already there. Yet, of course, the ADC converters have some disadvantages. From my perspective, the major disadvantages are two. The first important disadvantage is this, in fact, the input range. Usually the ADC has a limited input range between the power supply, negative and positive power supply. So positive power supply is maybe okay, it's so because we have 3.3 volts, so it's 3.3 volts at the top. But what's really sometimes a problem is the negative power supply. That in case of the ADCs, we've got the negative power supply equal to the negative power supply to the negative limit of a microcontroller, which is 0 volts. It's not negative, which means that if we want to use a sensor or an op-amp, operating amplifier, that generates a negative voltage, we have to take care not to break the ADC converter, because this ADC converter is susceptible to negative voltage, so it doesn't like negative voltage. When you take an external ADC converters, very often they can live with negative voltage and they can measure, so they are so-called bipolar. Unipolar and bipolar. Unipolar is from 0 to positive voltage, bipolar is from minus to plus. So usually we have a positive and negative inputs. Here we have only positive, so that's something I don't like. The second thing that I don't like in case of ADC converters is usually limited resolution. Although it did increase over time, so today in larger microcontrollers we can really get very nice, very decent 16-bit ADC converters with real resolution being about 12-bit, 12, 13-bit. So you don't count on having 16-bit resolution. So if you want to have really nice 16-bit or even or more, then you have to take external ADC. Don't count on 16-bit in microcontroller. But 12-bit is obtainable. You can get 12-bit, real 12-bit resolution. But still, in smaller microcontrollers, quite often we've got 8-bit or 10-bit ADC converters, which is not very nice. So these are pros and cons. And now the features of the ADCs that you can find in microcontrollers. So what can we configure? So two examples: ADC, simple ADC like we have in, for example, STM8, and more complex in STM32 in a moment. So what features can we have? Can we expect in a microcontroller? What features we should pay attention to when we analyze the ADC in a microcontroller? First thing, of course, we have to know the resolution very precisely. So is the ADC converter in our microcontroller 8-bit, 10-bit, 12-bit, 14-bit, 16-bit, because these are the options, or 24-bit, these are the options that we have. Then, what kind of conversions does it have? Usually a microcontroller, that's the block diagram. And usually, if we talk about a microcontroller, inside microcontrollers, we've got 1, 2, or 3 ADC converters. I haven't seen a microcontroller with more than 2 or 3 ADC converters. But number of ADC converters is not equivalent to the number of analog inputs. Because every ADC converter in every microcontroller I know has a multiplexer, analog multiplexer inside, which means that we can connect more than one signal, we can measure more than one signal by the ADC converter. So the ADC converter can measure more than one signal, but not simultaneously, not at the same time. In some applications, we need to measure a signal, few signals, at the same time. So not in this microcontroller. Here we can measure just one signal at a time, although we can measure those signals. So there, take a look, like 14 channels in this example, that we can connect different sensors. We can connect 14 different sensors. Or 13, let's say, from AN0 to AN2 and AN12, but we are not able to measure them at the same time. We can measure them sequentially, in some sequence. Usually it's not a problem, but sometimes we need signals to be measured completely at the same time. That's why, for example, if we are playing with brushless motors, then we should be able to measure the signals at the same time. That's why in the microcontrollers for brushless motors we've got 3 ADC converters. Not 1 nor 2, but 3. Each of them has its own set of input channels, and then we can play with it. What other things we can are imported? So then that's why we have single and continuous conversion modes, because we can play with the sequence of channels to be converted, and we can choose in microcontrollers. You can program the sequence of conversion. Should we convert only analog, for example, input 0 all the time, or should we, for example, convert 0, 1, 2, 0, 1, 9, 0, 1, 12, 0, 1, 0, 1, and so on, the sequence of conversion. And should we do it once in a single shot or constantly? So a couple of things here. Also, sorry, what is important is, for example, the clocking. How do we, what's the sampling frequency and what's the conversion time, and how we clock it. So here is a configuration, how it is defined. And of course, are we able to generate an interrupt? That's important. Yeah. Oh, an interesting thing, aside from ADC conversion, is in fact, but sometimes present in microcontrollers. Sometimes you can meet it in microcontrollers. Is the analog watchdog. We talked about the watchdog and window watchdog. So the watchdog that we are, these are software things, purely software things. But in some microcontrollers, in analog, allows us for such an option as analog watchdog. So don't be surprised to see it. Analog watchdog is that with ADC converter, we can configure the thresholds of analog voltage, and if our signal is within this threshold or outside of the threshold, then we get the interrupt. An event is being triggered, and something is wrong or good, whatever we said. So this is analog watchdog. If the analog signal is inside or outside certain range. In case of conversion as well, maybe let's skip it. Let's skip it a bit. Let's speed it up. Just 15 minutes. To show you, because I can talk really long about the ADC converters, but let's skip it a bit. There was a structure, a block diagram of the converter in STMX, so that you're playing with now this year. Next year I would like us, if you of course choose the embedded systems, to play with the ADC converter in 30-degree microcontroller, where the ADC converter allows you really to do much more. But still, take a look. This is just one converter, SARA ADC. All the other things are just around one converter, still one. So still is a configuration of one converter with 3 channels, for example, of analog watchdogs, with the triggers starting the conversion, a lot of triggers, with 20 channels as input, with also differential channels. And I would like to stop for a moment with this differential measurements. Why? Because in case of ADC converters, standard ADC converter like this one, doesn't allow, it has only single-ended inputs. Take a look. So we have single-ended input, and it goes to ADC converter, and there is just one line. So we can switch the multiplexer and choose any input, but still it's a single-ended. So if you want to measure this differentially, and why do we measure differentially? Of course, to reduce the noises, and of course to measure, for example, very precise sensors like on bridges, because you know you have sensors on the project, so you know how problematic it is. And it's a very good practice to measure differentially a sensor, because then we can really get below the noises, and we can really get the signal independent, for example, of the power supply, or with the dependence much reduced. But we can't do it here, because we have just single-ended input. But good ADC converters, and this one I'm showing you in the STM32 is a good one. Take a look, it does have a differential input. Analog differential, because we can try to connect it in case of the simple ADC converters, but then we have to manually then subtract the data, and it's still not really true differential measurement, because then we are doing it in time shift, because first we have to convert channel positive and negative and then subtract it. In better ADC converters, we've got the differential, fully differential, let's call it, where this is subtracted here, and then we measure only the difference, all are already analog, which means that the noises are subtracted in ADC converter. Yeah, what else do we have? We have plenty of nice things, but yeah, just to finish it. In case of ADC, what is important and what I wanted to show you, when you use how to use the ADC, maybe this one, how to use the ADC in practice. So during the configuration of the ADC, we have to first choose the clocking. Second of all, we have to choose which channels are to be converted and in what way. So single conversion, multiple conversion. So the simplest way is the simplest mode is shown here in the slide. So in the simplest mode, in a single conversion mode, we choose a channel and we choose a single conversion, and then we just start the converter. Usually converters have in a configuration register, and in the configuration register they usually have start bit, some AD start or AD on or whatever the bit is named. Then after the conversion starts, one channel is converted. So then first there is a sampling, because there is always a sampling phase. Then there is a hold phase where the measurement is going on because we have the successive approximation. And then the final result is placed in some data register. So that's how it works. So the data register should be here somewhere. Yeah, here it is. So this is this R data. So there is some data register. So we have we start everything, so the measurement is going on, and then the result is placed in the data register. So this is the simplest way that everything stops operating. We've got it. We receive an event that the result is converted. But this is the simple case. This is the simplest one. A bit more complex is so-called scan, multi-channel scan mode. Still single conversion, but in microcontrollers, quite often we need to measure a sequence of channels. And in microcontrollers, very often we have a set of registers where we can set a conversion order. Where, take a look, we can have multiple channels converted, same channel converted, conversion by conversion, or we can have different set of channels. Or we can say channel 1, channel 7, channel 1, channel 4, channel 1, channel 1, channel 7, channel 9, whatever sequence of channels we want. It's very nice in case of microcontrollers, and usually we have an access to this multi-channel conversion. Also single, which means that we start, conversion is going on through program sequence, and we get an information notification only when it finished. Where are the data? Usually it's two ways. In some microcontrollers, we've got as many registers in ADC converter as there are slots for this multi-channel. So even microcontroller allows for 16 different conversions for 16 different slots. Then we've got 16 different registers, and then the data are just placed in those registers, register by register. In other microcontrollers, we've got a special DMA configuration necessary. There is special DMA configuration necessary. DMA is a direct memory access unit. We'll talk about it this semester, next one, for automatic copying of data between various memory locations. And we have to configure the DMA, and then the data are placed not in registers but already in some memory space, in some memory area. So this is method number 2. Then method number 3 that we can find in ADC converters and microcontrollers, single channel continuous conversion. As you can imagine, very simple. What's the advantage, by the way? Because that's missing. Why to do it this way? Why not to make, let's say we have 2, 4, 6, 8, 4, 6, 8, 9. We have 9 conversions here. So what's the sense of using this method and not this method in case of multi-channel? Of course, we are offloading CPU. Because with using this method 9 times, we have to 9 times start the microcontroller. 9 times we have to react on the event, react on the interrupt. While here, we configure it once. We press button start, and then after appropriate time, we get an information. A certain number of cycles. Yeah, we can have also continuous mode. In continuous mode, we have to choose the sampling frequency. We have to choose the sampling frequency. Of course, it is limited by the speed of conversion, by the speed of this approximation. But still, we can slow it down. So we can't make it naturally faster, but still we can slow it down. So we can, for example, convert with 10 kilosamples per second, 5, 10, 20, or we can trigger it usually external. So we can trigger any microcontrollers and how fast it circulates or how fast the continuous conversion is going on depends on the triggering signal. Triggering signal. The source of trigger in microcontrollers, usually there are two sources of trigger. A timer, configurable which timer it is because it depends on the timer, or external pin. Two sources of trigger for this mode. And for the second one as well. So it's either a timer or an external trigger. Usually there is no timer usually in ADC converter. So usually it's not automatic. So that we just start that we can choose it within an ADC converter. Usually we need an external timer that when this finishes, then to push it further back on track. So of course the fourth mode that we have in microcontrollers is the multi-channel continuous conversion mode. So this is mode number 4. But of course that's not all. We've got more complex modes. We've got more complex modes available in microcontrollers as well. So in more complex ADC converters. Such modes, first of this, let's say advanced modes, because the first 4 were simple modes. One of the first advanced modes is injected conversion. Mode that is not always present, only in more complex ADC converter it is present. What's this? What the hell is this? It's like an interrupt. It's like an interrupt, you know? If we have a program, you know what the interrupt is. So we have a program, so we have the CPU is going to the program, it's going. Then we have an event and we have an interrupt. So for a moment, the processor stops doing what it was doing, grabs the interrupt service routine, and then processes the interrupt service routine. And when it finishes, it goes back to the original program execution. In case of injected channels, it's working completely the same. So the ADC converter is converting channel by channel, and then because there is a need to convert special extra channel, then the extra channel is converted. So that's what injected channel is. That's what injected conversion mode is. So we have a constant conversion of something, but because there was some need in the program to do an extra conversion of one channel is extra converted. So this is injected. We call it injected. No interrupt this time, but injected like that. So you should find injected conversion mode. Then another special mode of conversion is dual, regular, simultaneous mode. So this is when a combination when we have more than one ADC converter. 2, 3, as I mentioned sometimes. So then in 3 conversions, we will have 3 channels converted completely at the same time. So here the idea is that to use 2 converters completely at the same time. The most important is, of course, the triggers, so that we have synchronized triggers, and then we convert completely at the same time. This is useful, as mentioned, for special cases, for encoders, for motors, where we need to measure exactly at the same time, with the precision down to microseconds or sub-microseconds, the sampling precision. So then we sample at the same time, and then the data are converted, so the channels are converted completely at the same time, with different set of channels here, because it doesn't have to be constant set of channels, so the combination of channels may be, of course, different. But if we go this way, in some microcontrollers, we've got another mode. We've got another interesting mode that is sometimes useful. This is dual fast interleaved mode. What's the sense of it? Speeding up the conversion. Take a look. We convert. The idea is to convert same channel, but by 2 converters. Which means that if one converter is capable of delivering us 10 megasamples per second, second one also 10 megasamples per second, with this mode we can have 20 megasamples per second. The good thing about it, so of course you could say, we can have one, like we don't need dual fast interleaved mode. We can have standard measurement and measure with one converter and the other one. But the problem one separately, the same channel. But the problem is that when you do a standard mode, when you don't use interleaved mode, you will have a set of data from one converter, set of data of the second converter in different places in memory. Which means that if you want to use it, you have to manually take first sample from this batch, first sample from this batch, then second sample from this batch, second sample from this batch. With interleaved mode, all the data are being transferred to the same memory, which means that are interleaved. That's what interleaved means. That's interleaved. So they will be placed successively in memory when they are measured, which means that we will see, the program will see, we don't think about interleaved mode. We just get a nice set of data in a certain order. And the last, not the last, yet the least, much less important, is the slow interleaved mode, when we have a certain delay between them. That's maybe not so important. Dual alternate trigger mode, where that's also not so important. So don't really stick to this mode. It's just for curiosity. I don't want you really to remember this mode. That's not important. If you get so advanced in your DSP or signal processing duties, then you will search for this mode. I just want you to inform that something like this exists, where we have separate trigger for each mode, because here the idea is that it goes automatically. When one finishes, then the second one starts. Here the difference is that we wait for the trigger from either a timer or external pin. And really the last one I wanted to as well, not that important, is that we have injected version, but when we inject two converters, when we inject two channels. So as you can see, plenty of ideas. Some of them pretty useful, like the very basic modes, because three categories. So the basic, the useful, and fancy. That's the last one. Fancy modes. So the fancy modes are not really peculiarly useful, sometimes only, but the major ones and the advanced ones, yes, they are. So the injected modes and simultaneous sampling, they are pretty useful. So that's also why using an ADC converter inside a microcontroller is advantageous, because those modes are not really easy to be implemented. Those advanced and fancy modes from these two categories are not easy implemented by using the external ADCs. Okay, it's 3 o'clock, so that's it, unfortunately, for today. So we started the ADCs already on Wednesday. Monday. Thank you for today. See you on Wednesday.